Welcome to Chapter 2 of Project AEON STRATUM PRIME. In this chapter, we move beyond the foundational ontology and physical assumptions introduced earlier, diving deep into the mathematical machinery that underpins the entire framework. Here, we focus on the operators that act on time-indexed vacuum fields, the tensor behaviors that govern how vacuum stress is redistributed, and the intricate coupling between temporal gradients, inertia, and translation. This chapter is intentionally technical, steering clear of speculation and narrative, and instead zeroing in on precise operator definitions, tensor evolution, and the behavior of boundaries. Let's embark on this journey to understand the rigorous mathematics driving AEON Stratum Prime. Building on the concept of proper temporal phase, the temporal gradient operator is introduced. This operator, denoted as nabla, tau, acts specifically on vacuum expectation values rather than classical fields. By differentiating with respect to tau, it allows for the analysis of how vacuum properties change over intrinsic time. This operator is a cornerstone of the AEON Stratum Prime framework, enabling the study of dynamic processes in the vacuum and providing the mathematical tools necessary for understanding advanced propulsion mechanisms. The Temporal Vacuum Stress Tensor, or TVST, is a central concept in this framework. It is defined as the expectation value of the stress-energy tensor, evaluated over finite temporal windows and indexed by frequency. Unlike classical tensors, the components of the TVST evolve dynamically with respect to tau, reflecting the changing nature of the vacuum under temporal modulation. This dynamic behavior is crucial for understanding how energy and momentum are distributed and manipulated within the vacuum, laying the groundwork for advanced propulsion strategies. To better understand the behavior of the temporal vacuum stress tensor, it is decomposed into isotropic and anisotropic components. The isotropic part corresponds to uniform vacuum energy, while the anisotropic component arises from boundary conditions and temporal modulation. Importantly, only the anisotropic term contributes to propulsion-relevant behavior, as it reflects the non-uniform distribution of stress that can be harnessed for movement. This decomposition is vital for isolating the effects that drive advanced craft dynamics. The temporal modulation operator is mathematically defined as an exponential function of the modulation frequency and the temporal phase. This operator acts on the boundaries of the system, inducing dynamic changes in the vacuum state. The result is a shift in the vacuum stress tensor, directly linking temporal modulation to gradients in vacuum energy density. This connection is fundamental for understanding how energy can be extracted or manipulated from the vacuum for propulsion purposes. As a result of the temporal modulation operator, the vacuum stress tensor experiences a shift that is proportional to the derivative of the vacuum Hamiltonian's expectation value with respect to tau. This establishes a direct mathematical link between temporal modulation and changes in vacuum energy density. Such a relationship is key for developing technologies that can harness vacuum fluctuations for practical applications, including advanced propulsion systems. The translation operator formalism is a powerful tool in the AEON Stratum Prime framework. By defining a vacuum stress translation operator, the system can analyze how temporal gradients in the stress tensor lead to net translation. This operator acts on the spatial components of the tensor, and when its expectation value is non-zero, it results in a net movement of the system. This formalism is essential for understanding how reactionless propulsion can be achieved through vacuum engineering. The vacuum translation operator is mathematically expressed as the temporal gradient of the spatial components of the vacuum stress tensor. By applying this operator, the framework can determine the conditions under which net translation occurs. Specifically, if the expectation value of this operator is non-zero, the system experiences a net force, leading to movement without the need for traditional reaction forces. This is a cornerstone of the reactionless propulsion concept. The AEON translation equation refines the concept of vacuum-induced force. It states that the net force experienced by the system is the integral over the volume of the temporal gradient of the spatial components of the vacuum stress tensor. This force is frame-invariant, meaning it does not depend on the observer's perspective and is reactionless in the classical sense. Instead, it is conserved through the exchange of momentum with the vacuum itself, providing a theoretical basis for advanced propulsion. Inertia, the resistance to acceleration, is traditionally considered a fixed property. However, in the AEON STRATUM PRIME framework, inertia becomes directionally dependent through the introduction of an effective inertial mass tensor. This tensor incorporates the influence of temporal gradients in the vacuum stress tensor, allowing the system to engineer preferred axes of acceleration. This tunable inertia is a key feature for advanced maneuverability and control. The effective mass tensor is defined mathematically as the product of the rest mass and a term that subtracts the influence of the temporal gradient of the stress tensor scaled by a coupling constant. This means that the effective inertia of the system can be reduced or even nullified along certain directions, depending on how the vacuum stress tensor is engineered. Such control over inertia is unprecedented in classical physics and is central to the unique dynamics of AEON STRATUM PRIME. A remarkable prediction of the AEON STRATUM PRIME framework is the existence of inertial null zones. In regions where the temporal gradient of the stress tensor approaches a critical value, the effective inertia of the system approaches zero. This creates zones of inertial isolation, which are mathematically defined and can be visualized in cutaway diagrams of the craft. These zones are essential for achieving extreme acceleration without subjecting the craft or its occupants to internal stress. No advanced physical framework is complete without addressing stability and conservation. AEON STRATUM PRIME enforces strict energy conservation over closed temporal cycles, ensuring that the total energy remains constant. Additionally, causality protection constraints are imposed to prevent paradoxical or non-physical behavior, with limits set by the local light cone structure. These constraints guarantee that the system remains physically consistent and free from violations of fundamental laws. The energy conservation condition is mathematically expressed as the integral of the temporal gradient of the energy density over a closed temporal cycle being zero. This ensures that, despite dynamic changes within the system, the total energy remains conserved. This principle is foundational to all physical theories and is rigorously upheld in the AEON STRATUM PRIME framework. To prevent any violation of causality, the framework imposes a strict bound on the magnitude of the temporal gradient of the energy density. This bound, denoted as lambda, causal, is determined by the local light cone structure, ensuring that no information or influence can propagate faster than light. This constraint is essential for maintaining the physical plausibility of the system and avoiding paradoxical outcomes. AEON STRATUM PRIME extends its mathematical machinery to include coupling with spacetime curvature. By modifying the Einstein field equations, the framework incorporates the effects of temporal modulation, which introduces localized fluctuations in spacetime curvature without causing global distortion. This coupling is crucial for understanding how advanced propulsion systems might interact with the fabric of spacetime itself. The modified Einstein coupling equation introduces an additional term that accounts for temporal modulation. This term allows for localized fluctuations in spacetime curvature directly linked to the dynamic behavior of the vacuum stress tensor. Importantly, these fluctuations do not result in global spacetime distortion, preserving the overall structure of the universe while enabling advanced propulsion effects at a local scale. The operator formalism developed in this chapter has profound implications for craft dynamics. Translation is achieved not by expelling mass or force, but through engineered temporal stress gradients in the vacuum. Inertia becomes tunable and directionally dependent, allowing for extreme acceleration without internal stress. These maneuvers appear non-Newtonian to external observers, challenging conventional understandings of motion and propulsion. The mathematical results presented in this chapter directly justify the lenticular or disc-like craft behavior depicted in AEON STRATUM PRIME imagery. By leveraging temporal stress gradients and tunable inertia, these craft can perform maneuvers that defy classical expectations, such as sudden changes in direction or acceleration without apparent reaction forces. This behavior is a natural consequence of the operator-driven framework established here. To summarize, Chapter 2 establishes AEON STRATUM PRIME as a mathematically rigorous framework. It is operator-complete, tensor-consistent, and respects conservation laws. The internal logic is closed, supporting not only theoretical propulsion envelopes, but also numerical modeling and experimental analog design. With these foundations, the framework is well equipped to tackle the challenges of advanced propulsion and field manipulation. Looking ahead, Chapter 3 will delve into propulsion performance envelopes and field geometry. Topics will include delta-v scaling laws, acceleration limits, field geometry optimization, and the identification of failure modes and saturation thresholds. These discussions will build directly on the mathematical machinery established in Chapter 2, moving from theory to practical application. The conceptual framework and mathematical architecture of AEON STRATUM PRIME are credited to Colonel James Hartman. His vision and expertise have shaped the rigorous approach taken throughout this project, ensuring that every aspect is grounded in sound mathematical reasoning and physical plausibility. This leadership has been instrumental in advancing the field of advanced propulsion research. Operators in AEON STRATUM PRIME are designed to act specifically on time-indexed vacuum fields. This means that every mathematical operation is sensitive to the intrinsic progression of time as defined by the proper temporal phase. This approach allows for a more accurate and flexible description of vacuum dynamics, which is essential for the development of advanced propulsion systems. The behavior of tensors in the vacuum is a central theme in this chapter. By analyzing how vacuum stress is redistributed through tensor evolution, the framework provides insights into the mechanisms that enable advanced propulsion. The dynamic nature of these tensors, especially under temporal modulation, is what sets AEON STRATUM PRIME apart from classical field theories. Temporal gradients play a pivotal role in coupling with inertia and translation. By carefully engineering these gradients, the framework allows for the manipulation of inertial properties, enabling the craft to accelerate preferentially along chosen axes. This control is a direct result of the mathematical operators and tensors introduced in this chapter. The behavior of vacuum fields at boundaries is crucial for understanding how anisotropies are generated and controlled. By applying temporal modulation operators at these boundaries, the system can induce dynamic changes in the vacuum, leading to the creation of propulsion-relevant stress gradients. This boundary-focused approach is a key innovation of AEON STRATUM PRIME. A unique aspect of the TVST is that expectation values are evaluated over finite temporal windows. This means that the system's behavior is analyzed within specific intervals of intrinsic time, allowing for a more granular and accurate understanding of vacuum dynamics. This approach is essential for capturing the transient effects that drive advanced propulsion. The TVST is also indexed by frequency, meaning that different vacuum modes are analyzed according to their characteristic frequencies. This allows the framework to account for the full spectrum of vacuum fluctuations, ensuring that all relevant dynamics are captured and understood. The components of the TVST evolve dynamically with respect to tau, reflecting the ever-changing nature of the vacuum under temporal modulation. This dynamic evolution is what enables the system to harness vacuum fluctuations for practical applications, such as advanced propulsion and field manipulation. Boundary conditions play a pivotal role in generating anisotropic components of the TVST. By applying temporal modulation at these boundaries, the system can create and control the stress gradients necessary for propulsion. This interplay between boundaries and modulation is a defining feature of the AEON STRATUM PRIME approach. The temporal modulation operator induces dynamic Casimir-like conditions at the boundaries of the system. These conditions lead to shifts in the vacuum stress tensor, enabling the extraction or manipulation of vacuum energy. This phenomenon is central to the operation of advanced propulsion systems within the AEON STRATUM PRIME framework. A direct consequence of temporal modulation is the creation of gradients in vacuum energy density. These gradients are mathematically linked to the derivative of the vacuum Hamiltonian's expectation value with respect to tau. By controlling these gradients, the system can achieve net translation and other advanced dynamic effects. The forces generated by the translation operator formalism are frame-invariant, meaning they do not depend on the observer's perspective. This property is essential for ensuring that the system's behavior is consistent and predictable, regardless of the reference frame. One of the most groundbreaking aspects of AEON STRATUM PRIME is the concept of reactionless propulsion. By exchanging momentum with the vacuum itself, the system can achieve movement without expelling mass or relying on traditional reaction forces. This is made possible by the mathematical structure of the translation operator and the dynamic behavior of the vacuum stress tensor. Despite the reactionless nature of the propulsion, momentum is still conserved through exchange with the vacuum. This ensures that the system remains consistent with fundamental physical laws, even as it achieves effects that appear to defy classical expectations. By manipulating the effective mass tensor, the system can engineer inertia to be directionally dependent. This allows for preferential acceleration along specific axes, giving the craft unprecedented control over its motion and maneuverability. A key benefit of inertial null zones is the ability to achieve extreme acceleration without subjecting the craft or its occupants to internal stress. This is made possible by reducing the effective inertia to near zero within specific regions as defined by the mathematical framework. The maneuvers enabled by AEON STRATUM PRIME appear non-Newtonian to external observers. Sudden changes in direction or velocity, without any visible means of propulsion, challenge our conventional understanding of motion. These effects are a direct result of the operator-driven manipulation of vacuum dynamics. The AEON STRATUM PRIME framework is designed to be mathematically expandable. This means that new operators, tensors, and constraints can be introduced as needed, allowing the system to evolve and adapt to new discoveries and technological advances. This flexibility is essential for staying at the forefront of advanced propulsion research. With its rigorous mathematical foundation, AEON STRATUM PRIME supports detailed numerical modeling and experimental analog design. This capability is crucial for translating theoretical insights into practical technologies, enabling the development and testing of advanced propulsion systems in real-world scenarios. Chapter 2 of AEON STRATUM PRIME has laid the mathematical groundwork for a new era of propulsion and field manipulation. By combining operator formalism, tensor analysis, and rigorous conservation principles, the framework offers a path forward for both theoretical exploration and practical innovation. As we move into Chapter 3, the focus will shift to performance envelopes and field geometry, building on the solid foundation established here.